Hey guys, welcome to another episode of Robo Papers. Super happy today to have Chaoqi, one of the authors of this paper called OAT, Ordered Action Tokenization. Thank you so much for making the time, Chaoqi. Maybe as a start, if you can share a little bit about yourself first before we dive into your paper.
Yeah, certainly. Hi, everyone. So I'm Chaoqi. I'm currently a senior undergrad at UIUC, and this project is done during my visit at Harvard University, working with Yilu and other postdocs and fascinating visiting undergrad there too. So in this project, it's really about like working on action tokenization, and I will discuss more in this session. Yeah. So should I start or?
Feel free to start. Yep.
Yeah. Okay. Great. So, uh, so in general, what we are interested in is action tokenization, and why are we interested in action tokenization, and why action tokenization is still necessary? I think in few sentences, basically, for example, these days the VOA policy, like fine tuning from the VOM policy backbone. I mean VOM backbone. They are like all using diffusion flow action expert, but why in this case we still want discrete representation, for example action tokens? I think the main reason is we still want the signals to we still need one strong signals like discrete action tokens to for fine tuning the VOM because we've seen that the signal from the continuous diffusion flow action expert head is very weak. It's very weak signal to supervise the VOM backbone. So for example, in the winning solution of the behavior challenge last year, they also observed that by adding auxiliary loss on the discrete action representation, in the case fast tokens, they observe a significant better pre-training. And also, I think recently we also see post-training on these discrete representations boost performance and also the convergence rate. So after the motivation, I hope everyone is convinced that the action tokenization itself is not necessarily, I mean, it's not a implementation detail or some minor detail in implementation, but it's something very important that boosts pre-training. So we propose this auto action tokenization, which we start by first talking about what are some key properties that we want our tokenizer to have. So first, we want the tokenization mapping T to have a reasonable compression rate. So let me explain what is reasonable compression. So for reasonable compression, I mean, I intend to say, so we want to strike a balance here. So a good representation that we achieve is we want to remove some redundancy, but not too much. So some compression algorithm is extremely achieve extremely high compression rate, but that's not something we want. So a good representation, a reasonable compression is that we want to remove information that's unnecessary and not useful. And the second property we are very interested in is we want to have this decoding function as a total function. And a total function by its definition is we want
Could you give an example of what? Sorry, I think we're having some internet sync issues. I think I was wondering, could you give an example of what information in an action is not useful? Like, what is that? What is an example of like what would concretely be useful tokenization?
I don't have a good example here, but in general, like there's always some redundancy in the action chunk, but I'm saying that we should not remove all of them, but maintain some structure there that we can have our, yeah, right.
So it'd be like noise, or like removing noise or removing.
Yeah, for example, noise. Yes.
Small errors in like a finger joint position that doesn't matter, stuff like that. So that's the kind of thing that. Okay.
Yeah,
makes sense.
Yeah. For example, like those. Yes.
Okay. Thanks.
Yeah, and also the second property we list here is like the decoding function should be a total function by the definition that all the token sequence generated by the VOA policy or basically autoregressive policy should be decodable, should be always project back to them reasonable action chunk. We have this property list here. I thought like this should be a must-have property, but we listed here simply because we have this fast token that's not always decodable, so we listed here. But this should be a must-have property for or tokenization, I guess. And I will also
Sorry,
dive
Chaoqi,
into
Chaoqi, I have a quick question.
yeah.
Could you give an example like so in the case for the previous work fast, you mentioned that there are some instances where it's not totally decodable. Like concretely, what happens when there's some actions that cannot be, decoded back to like concrete actions.
Yeah, let me
Those
explain
cases.
like why we have this undecodable issue and what happened and what are some um method to try to mitigate this. So if we go to fast tokenization paper, we see that what they did is basically doing a Fourier transformation to get a frequency matrix, where the frequency matrix is a fixed size matrix. So there are n, so basically action dimensions, say seven rows. Each row is representing the the frequency coefficient of that particular action dimension, and there are n columns, which is where n is a hyperparameter. And after that, they just flat this matrix and doing a byte-pair encoding, where we all know that byte-pair encoding is a variable length encoding mechanism. So in this way, so basically it give you something like this. So it has the first byte, second, and continue. First token, second token, and continue, and these concatenate to be the underlying coefficient you have. But each of them are like have variable lengths. So in that way, so the number of total coefficient you are going to extract from that fast token sequence, it's a variable. It's variable length. You just cannot make sure it achieved this fixed size frequency matrix. So in that case, we have either more more frequency coefficient or less frequency coefficient. So that's the reason why fast is not always decodable. And some very naive way to mitigate this is if you have your fast token produce longer frequency coefficients, you just drop out from the tail, some of them. Or if it's it's not achieving this untarget number of coefficient, you just pad with zeros. This is also mentioned in the Hugging Face discussion in the fast repo. The other also suggests don't do this, so don't do dropout or pad with zero, because it's very unreasonable to do so, because you have this coefficient in frequency domain. You just pad zero. You are pad zero to some basis function. Also doing job, it's like you can have this mismatch as I mentioned here. For example, you don't really know like if the action for the joint, say 3, it's shifted to 4 or something. So this is a very unsafe way to do that. The other of us also discourage others to do this rounding or padding thing. So that's the main reason. But doing this job but doing this padding there or dropping from the tail actually can improve some success rate, but that's just very unsafe to do so. In real world, we don't want to do that. Yeah. So
Okay,
that's what I mean by the total decodability. Yeah. And lastly, what we want is this ordering thing, which is also the main theme of the paper. So why do we want ordering? It's really about we want this modelability. So I'm thinking that like traditional compression algorithms really care about two axes, whereas compression rate, and we also have this like reconstruction fidelity. But I'm saying that like in the era of generative AI, we should also think about the modelability, which characterize like how challenging it is that this representation distribution to be modeled by the autoregressive diffusion, these generative model paradigms. So I think that that's what I mean by modelability. And this word is first introduced also in the blog by Sandra Dellerman here, where this word is also coming from some literature envision that we have this perceptual axis, and we just conclude that modelability. Why do we so to improve modelability of autoregressive models? A natural thing is to have this ordering. This has been started since like 2014, where we first have people have, and I mean there's a really large set of literature that's saying that when we have ordering for autoregressive models, we have better performance. So that's a very nature intuition that if we have our action token to have ordering, then we probably can boost the performance or stabilize the inference of the autoregressive policy inference. So that's why I try to inject ordering. And to have this ordering injection, what we did is having the paradigm, I mean the diagram here. So we use registry to extract the action tokens, to extract information from action tokens, and then we do this nested dropout from the tail. So basically, at the training time, we just sample a random number smaller than the total number of the registers and drop out them from the tail and ask the decoder to reconstruct based on the prefix. And in this way, we force our decoder to reconstruct given whatever prefix it has to. So for example, given only one token, it already has to predict something. And in this way, to minimize the loss, it has to predict the pattern has the highest frequency in the data set, because we know the action distribution is highly non-uniform, and it has to predict the general pattern that minimize the overall loss. And it's sequentially, like we have second token, third token, and when we have more token, we have more capacity. It has more capacity to model less frequent patterns, action patterns. So this is how we have this implicit ordering injection. And with these old token, we can then have our autoregressive policy trained on this token space. So it basically have this inference loop, like given the start of the special token beginning of the sequence, we can we can step our autoregressive policy once to get our first old token, and just given this token, we can already decode that to some reasonable but less fine-grained action chunk. But maybe you don't want to stop here. You want to get a finer action chunk. You can just continue the autoregressive loop iteratively to get more old token generated, and you can just decode them whenever you want. So that's what I mean by prefix detokenization and anytime inference used in my paper. And one very nice application experience I would like to discuss is this old without ordering underperform. So the paper's main contribution is really to emphasize the ordering is really important. And we see that in this table, we add a new row X, which represent we have this entire, have the exactly the same training pipeline of the old tokenization figure I just shown, but we just don't have this nested dropout from the tail. And for these old 1248, it's saying that we have this dropout, and in the inference, the task execution, I'm just using one token, so one autoregressive step, two autoregressive steps, or 4 and 8 steps. And the quest is one of our strongest baseline. It's also a learning-based quantization method. We see that like with this nested dropout, like we only half the compute due per inference, which is using 4 tokens, we are already almost the same as the our strongest baseline here. But suddenly without this nested dropout, so without ordering, we have like a huge degradation in the performance. So that's a problem here, because Quest has some structure, but without ordering, it's completely unstructured. And I will explain like why Quest has some structure. It's basically like they're doing convolution to have a reduced horizon policy learning problem. And yeah, I think basically that's all of the results, and we can have more discussion on related methods in action tokenization, and my general thoughts and other future thoughts on action tokenization as well.
Yeah, Chaoqi, I know you have on the site some video as well. Would you like to go through some of them? So,
Oh yeah, sure.
people get maybe a visual understanding of some of this.
Yeah, this is one of my favorite visualization. So in this case, I'm just having a 7 dove KUKA arm, and I have a motion planner that's just generating random trajectories in the workspace, and I'm asking it. And then I train my tokenizer on this and try to reconstruct with the different number of tokens. And you can see like with one token it's a very coarse, very basically meaningless trajectory. But you can see the general motion pattern is correct. So look at the ground truth. It's basically from the far side and moving to the closer side, and that's also the thing that the with one token is trying to do. And with two tokens, like the motion is much more obvious and the magnitude is larger. And with 4 token, we can almost like faithfully reconstruct this, and also 8 tokens something even better. And another example here. You can also I'd like to let interesting audience to try this. You can just drag and try to compare these. Yeah. So we also have some real world execution videos, but I don't think there's huge difference visually by looking at these videos. So I try not to waste time on these videos. Yeah.
Still
Yeah,
nice to
because
see
like
that there's not much difference.
yeah,
That's
there's not
that's
much
good.
difference
That's a nice
because it's
sign.
not like yeah, I mean,
Yeah.
like it's not like having a new modality, like say tactile sensor, that you can see huge a behavior difference visually. It's just like an algorithmic improvement. So we almost have quantitative results instead of like qualitatively. You have a huge difference. Yeah, I hope that makes sense.
Yeah, you mentioned somewhere in the paper that, like, I think given that, like, you if you only have one token, then you have a very coarse, let's say, representation. But then if you have more, and then you get very, very granular. So, and you mentioned something about, actually then this allows, in practice at inference, you might have different compute, and maybe you run out of compute a little bit, but you get away with less token and still kind of get the job done, right?
Yeah, so we show our results in the appendix that you can see we have compared all the like using 1 token, 2 token, 4 token on different benchmarks. So yes, we can finish most of the tasks with even like 1 or 2 tokens. Like regarding the compute and any type of inference, I think that's also discussed in the discussion, and I'd like to discuss this too. So I think in the blog from Pi Intelligence, the blog on the real-time chunking, in the very intro paragraph, they mentioned that in the future, the robot policies would have to have some property that it can pause and think if the situation is very complex, and if the situation is very simple, and just you can know what to do very shortly, then like we can execute fast, pretty fast. But when necessary, we have to stop and think. So I think with out we potentially have this property. Currently in the paper, I only have 8 tokens. In most VOA and I mean tokenization for VOAs, they have like 16 or more tokens. So with that, we can really have this pause and think, and like for example, only step 2 tokens to get a very fast result, something like that. So that's one thing. But one natural direction and a question to ask is like, how can we decide like when let the robot to pause and think, and when let the robot to execute and inference really fast? So this is mentioned here. So from my perspective, I think there's definitely a lot of engineering trick you can do to have this behavior. Say you can have a standalone multi-layer perception OP that trying to predict the number of tokens you would want for this inference condition on say current observation. And I think this would work. For example, if the observation showing you just doing transportation like commute in the air, then you probably just using 1 or 2 token would suffice. But if the observation showing that you are doing precise and contact rich manipulation, so you are already doing the grasping, then you probably want to have full token reconstruction. But I think one very exciting direction is not to have this engineering trick, but to really think about how can we doing the estimation of the intrinsic complexity of action chunk online. So by that I mean, I want to give an example first. Is at here you will realize that using 4 tokens for this turn off sync task is actually having higher success rate compared to using 8 tokens, which makes sense to me if you think about this. It's really because using 4 tokens already can faithfully reconstruct the action chunk needed for this task, but you are forcing the autoregression model to step 4 times more, and then it could compound a lot of errors there. So it is like a must-have property for the VOA or policy model to know like when to stop making more errors and when we already have faithfully reconstruct or encode represent the action chunk. So that's what I mean by the why we want this online estimation of the intrinsic complexity of the action chunk, and hence we can have our autoregressively to be truly when needed pause and think, and when not necessary just inference really fast to get the result.
Yeah, I'm trying to imagine a real world case where, let's say, I'm bending down to tie my shoelace. When I'm bending down, reaching my hand to the shoelace is probably maybe 1 or 2 tokens. It's good enough. But then once I touch a shoelace, probably I need 16. Would you be? Is that kind of what you mean?
Yeah, that's
Okay.
what I mean. That's some like, because like shoe tightening is like the action chunk should be highly non-trivial, because say consider the case that you are just transport your any vector your robot arm in the air. Then it's very simple, very naive. Basically in general very smooth action chunk. So the intrinsic complexity is very low. For example, you just given the first waypoint and the last waypoint and just doing the interpolation within them, that would maybe already work. But for shoe tightening and other contact-rich and precise manipulation where you within that action chunk there's a lot mode change and rapid change in the waypoint, then you probably want to have more faithful reconstruction. Yeah.
So I guess this is future work, but like I think that's really interesting. But how do you think you could train it to like to know how long the sequence should be? And this is like how precise the specification for the action is, right? It's not like how long the action chunk is. It's just like yeah.
So I do looked into the like how can we do this estimation online during the project, but I think due to the time interest, I didn't dive deep into this. But I think there's
so it's the next step for you.
Really nice. Yeah, I think there's some thoughts on this part. Especially I looked into this paper. Let me share how they did this. They did this in image generation, and they can do complexity estimation by it's loading.
So it's not as simple as just like predicting a stop token or something.
Yeah, it's not a very simple idea. So I think in short, it's basically doing this. So in the paper, they're doing this. So they have this arrow conditioned reconstruction pipeline, the one training the tokenization. So it's they have another float variable, say the desired arrow is 0.1, for example, in terms of a one loss for image, for example. And given this arrow, the training looks like this. So it first has a budget term, say using 8 tokens, and it compute the loss, like the reconstruction loss given 8 token budget, and then to try increase the budget to say 10 token and see if the reconstruction arrow goes down. If it goes down and it's not approaching the threshold 0.1 we are given, the arrow threshold, then it increase the budget to 10. But if also like in the training they also try to reduce the token budget, say from 8 to 6, and given the reconstruction arrow of 6 tokens, if it's not like decrease, if the loss is not increasing, so basically reducing token budget from 8 to 6, you can still faithfully reconstruct the image in the case. Then probably you would make you can next time you can just using 6 tokens. So this is how the training looks like. So you are kind of like doing a line search on this token budget axis and then see which of them like can
So this
faithfully
but this takes like
satisfy
a
the error.
but this takes like a fully trained tokenizer. So once you have your tokenizer fully trained, then you can train this second model, which can
Oh, they're
predict
doing this
basically.
simultaneously.
You can't do it simultaneously.
Yeah,
Okay, cool.
Yeah, they are doing this complexity estimation and the tokenization training simultaneously. I haven't dived into the paper too much, but I think that's a general philosophy they're trying to trying to propose. Yeah.
Yeah, really cool. So this will give you, at least in part, this quick capability to like think as long as you need to, the anytime inference kind of right. Exciting. So this is like kind of the next research direction for you.
Yeah. Oh, by the way, like in traditional like VQ literature, like when they like having say a fixed say a 16 token, which is like you have to step your autoregression model to generate 16 tokens to reconstruct.
Yeah.
But in our case, and also like some literature like on multi-scale VAE, they have this manually crafted skill on this part. But in our case, I'm saying that the allocation of our information, allocation of the information in the latency, purely like it's not manually crafted. So for example, you can have this say 32 registers. In fact, you maybe only need 8 registers, but you can have an overestimate of the register you needed there, and you can train it, and the training pipeline would tells you only need it will only allocate all the information to the first 8 tokens, and the rest of them are just basically useless. So this is a very smart and an elegant idea that you can have some estimation on the number of tokens you set before training, and after that you can just drop out those tokens.
Yeah.
Yeah. So you can have like for example like having how many number of tokens in traditional VQ method, it's a hyperparameter that's very sensitive to tune. But in our case, it's not. You can have an overestimate, and you can then just drop them. It's fine. Yeah.
Yeah. Do you think that that'll so like how do you think things like this scale? So let's say, I'm curious because like obviously you're trained on like Libero and so on, like these small data sets. Like there exists these large data sets out there. Like if I had 10,000 hours of robot data, how many? I mean, I know there's no real way to answer this, but how well do you think this kind of thing would scale to like 10,000 hours worth of robot data with different actions?
Yeah, that's a good point. Like due to limited resources, I'm still like in a school lab, so I really don't have that experience. But I think that's definitely one very interesting question. Recently, I'm talking to researchers at TI and FAR to discuss like the scaling of this method, which I think like we have a good hope. Like I think I don't see a strong like bottleneck on like why this one scale, because such ordered representation learning has been applied also to other modalities, say images and video, where they have even a significantly larger encoder and decoder and the code book size. So I don't see a cell there for this method. Yeah.
Can I ask how? Sorry, if Michael is going to go, but sorry, like okay. Can I ask how the codebook size impacts inference time, or does it? And like how does like I guess the autoregressive, the fidelity with which you reconstruct the action for sure would impact inference time, right? Can you tell me a little bit about this? Like, because you were comparing to diffusion policy, which of course.
Yeah, sorry, can you repeat it? Because like it's a bit like the connection is not that stable.
Yeah, the connection's a little choppy. Inference time.
Yeah.
So like how do these different decisions impact how long, like how quickly can you execute a policy, right? Like can I execute it at 5 hertz or 10 hertz, or like is this also a knob that I can tune by changing how many autoregressive steps that I take for rolling out like the tokens? Does that question make sense?
I don't quite get it. Like, do you mean how, like, during inference, like during?
Yeah. When I deploy the robot, I'm curious. Like, so, like, this is an issue. Like, we've talked to researchers before about like how long, like, getting robots to to like execute the policies quickly, of course, right? Like this is like sometimes inference can be very long, right? Especially with a large model. So like a VLA. So like how is that something that like I would think that if I only am regressing 1 token versus 10 tokens or something like that, that would make a difference to this. Like will it be faster? Can I run the robot policy in a tighter loop to perception? Does that question make sense now? I'm sorry if I'm explaining this poorly.
I think
Maybe
I
Michael
get
can
it.
try if it doesn't.
Yeah,
sorry.
I think I get it. So at this time, like deciding at deployment time, like deciding how
Yep.
many autoregressive sets it's just a preset number. So I don't have
Right.
a way to set that. So it just like during experiments, I'm asking a policy to just
Yeah.
step 1 or step 8 times. But
Yeah.
definitely like yeah. So I don't know if that's your question. And
yeah.
I also showed
Oh no,
the
it's like, but how much
comparison.
less time does it take to execute 1 step versus 8? That's that's my question, I guess. But just
okay.
right.
Yeah, so I show inference time here because the policy model is very small
perfect.
in the case, so you don't have a huge improvement. And also I'm using KP cache,
Right.
so so it's almost like at least twice, I mean twofold, in the inference time, like from 1 token to 8 token. Yeah, it's not like 8 times. Oh, by the way, I think the majority of the time, like when I do the profiling of the inference code, it's really about the observation encoding. It's a bottleneck there. So
Yeah.
observation encoding is taking the majority of the time. It's not the autoregressive policy in the case because I'm using small policy.
But like as your policy got bigger, I could see that this could be conceivably like this going back to the original question, because I mean we're curious about scaling it to 20,000 robots or something, or hours of data.
Yeah.
In that case, like huge model, like would you expect this to make a big difference? Or
yeah, I expect there to be a huge difference. And yeah, and also regarding like to scale this to different embodiments and different data sources, I think there's a very nice quantization paper. Not this one. Yeah. You can have these labels, embodiments labels, also condition like for each embodiment here, for example, to have this for scaling. So yeah, but so
embodiment information too. So
yeah, you
specific
can also
embodiment.
encode your embodied information, encode your the action chunks. For example, if it's 10 hertz or 30 hertz, or if it's like the action chunk is in terms of period is like 1 second or 3 seconds. You can always put all of this information into the encoding to have a better training. This paper just comes out like yesterday. Yeah, so this is a very nice paper on ablation on action tokenization. And they have this scaling of vanilla VQVA style tokenization, but the condition on this information. Yeah, but I think like action codec. I'd like to share some more thoughts on the action tokenization part, if there's no further question.
Yeah,
great,
please, of course.
So I think if you go to the very beginning, like where we have this VQ behavior transformer, what they're doing is just doing a very naive way, which is just having a MLP. And for the action chunk, for action chunk, the matrix HA times DA, you just flat them and as a single vector and feed it to the MLP, which is obviously a way that's very nonsense, because you are breaking the structure along the temporal axis. And then later we have the quantization. I mean the Quest paper that they're doing convolution along the temporal axis. So in general, what we are trying to do is reducing the action dimension from DA to the latent, and from the temporal axis we want to reduce from the H action, horizon action horizon to latent horizon. And to do so, what they are trying to do, and also that's also what would be used in the RDT2 paper, if you are familiar with that that paper. Both methods are using convolution to reduce the temporal axis from action horizon to latent horizon. And actually, I do think using convolution makes much more sense, because in this way, you have like due to the convolution's spatial receptive. So each latent token is aggregate some information from its adjacent actions. So in this way, we have they call this skill token, which doesn't make too much sense, but a little that each latent in this case is correspond to a few action chunk, a mini action chunk, so a few actions. So that's previous VQ method, like they use convolution, and more recently using our old method, we have this learnable registers to extract information, and also using the fact from Jianlan Luo's group. They're also using registers to extract information, and also the paper released yesterday, they are also using learnable register, which is learnable embedding here to extract information from action. So I'm trying to infer that we have this history here. I'm trying to say that we are evolving in the representation learning part, which is the encoding learning part. Yeah, because representation learning and reconstruction are two tasks. So I'm currently focusing on the representation learning part. We have seen this from just naively break the structure to flat into a single vector and pass feed into a MLP to we try to preserve some structure along the temporal axis by doing convolution. And more recently, we have this using learnable registers to extract information from the action chunk. So so I try to make a point here. And yeah, and also like I try to say that this nested dropout can only be applied if we have this register or learnable embedding way to tokenize. So it cannot be used if we are using convolution because that doesn't make sense. Because in convolution, the tail token, maybe say the last token, it represents some information for the mini chunk action chunk at the very end. So if you just drop them, you are losing the information. So it doesn't make sense if you try to apply nested dropout for ordering on this type of encoding method. But in old or other like using registers for encoding, you have your register to extract. So all the register can see the information from all the actions. So you need to have your register to attend to the entire action chunk to apply nested dropout. And nested dropout is something I think agnostic to encoding and decoding method, given that you have this you have your encoding that attend to entire action chunk. So so in this way, I think I'm not expecting OLED itself to be the final answer, but I hope like in future action tokenization design, nested dropout is just a like in place plugin extension that you can apply for a better performance. Yeah.
I have a question going back to very early on when you were talking about like the need for action tokenization.
Yeah, certainly.
You have this, I think one of the charts that kind of show diffusion and then also OAT, right? So like, how do you think about these like diffusion or flow policies that, let's say, do iterative sampling, versus auto-regressive policies that are, generate very discrete tokens, right? So what do you think are the trade-offs here in practice?
Yeah. So I think I do think like it is. Oh, let me show the general big picture here. I like this figure. So I think in the future, the discrete action representations, say tokens, my internet is a bit bad, but in general, like the discrete action representations, say tokens, and the continuous action representation, decoded by using flow or diffusion, they have to coexist because in the report. This is a report from the first place solution for the behavior challenge last year.
Yeah.
They have mentioned that not only a time but many times that like having fast token it's a way to boost inference. I mean pre-training. For example, this is how they do this. They have this auxiliary action token, fast token that they are using here. So they do not apply action tokens during. I mean it's just auxiliary loss, so it's not used for to be executed. But they just have this another channel here to have auxiliary loss to boost training. And also, if you are familiar with the RDT2 paper, in their stage one, the given VM, the stage one is to do discrete action representation, use action tokens for the the stage 1 pre-training. So given a VLM that's never been used to predict action, they first use they first ask you to do this action token prediction task. So in this way, it steer the VLM to be more like a VOA. And then in second stage, it just throw away the action token and replace with a continuous action expert and ask that, and then supervise the flow or diffusion head. So that's a stage 2 thing in RDT2's solution, and it's a joint thing in the behavior 1K winning solutions case. But I don't know, like,
why does it make such a big difference? Why is it so useful? Why does it make such a big difference?
Like having discrete representation.
Yeah, having the auxiliary like fast token output.
Yeah, because because we have seen that like the signal from the diffusion flow when supervising them is can potentially even harm the VOM, even if not like being useful. But like having this discrete action tokens, we can apply like what we are familiar with, like training AOM or VOM. Like we have this discrete token, so you can just we know how to train them well. Yeah, but I think there's very little literature on using action representation in post training, say with RL, because like I once talked to Drew, who was a research scientist at Google DeepMind. He told me that at General Robotics, they observed that during post training, with RL on the diffusion of flow head is basically nonsense. So I think during post training, we probably also want some discrete representation there. Yeah, so I think like robotics people are like in very early stage on like training foundation model. Like I think like in classical LM or VLM, they have this multi-stage thing, like first stage, second stage, next stage. So I think like in the future, like we definitely have a lot of stages, and I do see a place that discrete action representation is still necessary for like early stage training.
Yeah, that makes sense.
Fascinating stuff.
Yeah.
Yeah, so I guess you kind of allude to this earlier on, like, you know, kind of future where you probably want to do something to explore how to maximize the online, like figure out how to dynamically figure out like how many tokens to use, like, or what's the right amount. Let's see, any other future directions that you'd love to explore besides that?
Yeah, I think like I think there are a few axes. So I do think there's there are still a few things that we can improve in action tokenization itself. I will explain this. And second part is given a training tokenizer, action tokenizer, how can we use them? Use during pre-training and post-training is still underexplored. And third, like condition on these action discrete representation. In this case, it's not conditional on the fast token, but maybe what if we have this token also like action expert here condition on these discrete representation. So in the case, like given this, so in OAT specific case, like condition on the only the first token, would that make the policy much more multimodal? And what if like condition on 4 or 8 tokens, would that make the policy more unimodal? Because like you have more specified trajectory for that. So that's one fundamental question I'm also very interested in. So also like let's go back to the first point, like what do I mean by they are allowed to understand to improve in action tokenization itself. It's yesterday the paper, they have a very nice observation. A metric they made is the overlap rate. So basically, given the action chunk, say you are predicting 32 actions, given the action from 1 to 32 and the 2 to 33, so given the adjacent action chunk, and you let your encoder to encode that, you get two action token sequence, and you compute how much overlap rate you have for adjacent action chunks. And you realize very naive way and a very vanilla vector quantization training or binning or fuzz, they have very, very low overlap rate. But high overlap rate is actually very useful. That's highly related to what I mean by model ability. With high overlap rate, you can see the latent space of the I mean, essentially the policy makes much more sense compared to if you have a very low overlap rate. So yesterday I read this paper and I did
That
something.
makes more sense. You mean it's more contiguous, meaning that everything there's more like
Yeah.
You can interpolate between the different spaces. It's more contiguous.
Yes.
Yeah.
Yes.
Right.
So yesterday, I after I read the paper, so yesterday evening, like midnight, I read this paper and I did some experiments on oat and fast and quest. So my observations, fast is like 20% overlap rate, which is extremely low, and for quest and oat without having auxiliary loss. So in the paper, they have proposed two auxiliary loss to help improve the overlap rate, but very naively, like without such loss, we have quest and oat around 60%, which I think is quite decent. Oat is slightly better compared to quest, because in the case like first to understand why oat is slightly better in overlap rate compared to quest, we can first look at the very naive case of binning. So when we do binning, when we have this 33 action, the last action, that would result in say if the action dimension is 7, so we have completely 7 different actions. And also for the very first action, we also have another 7 different tokens. So in this way, like we have this binning being extremely low in the overlap rate. That would be the same for quest, because quest is no much difference compared to binning, but just a reduced version of that. So it's just pack a few actions into one latent, pack another few chunk of actions into a latent. So in this way, at the very tail, that we would always have a different latents there. So that's why I mean that's why that explains like why quest has slightly lower overlap rate without having further auxiliary losses to improve the overlap rate. But in the paper, like the overlap, so I think the one research direction is really like to improve action tokenization is to look at the overlap rate. So in their paper, they realized that overlap rate and the reconstruction fidelity are two axes that we cannot improve simultaneously. So we have to achieve balance there. Naively training, say using residue vector quantization RVQ to have a very superior reconstruction fidelity would naturally lead to very low overlap rate. But we also want the overlap rate to be high to let the autoregressive policy to learn. So it's really interesting to think about this, like how can we achieve a balance there? Yeah. So I think that's one interesting direction for action tokenization research itself.
So I'm curious. So that's really interesting. I'm curious how this all would plug in. Like you mentioned RL earlier, like as one potential advantage. So like, do you think there's a role for like learning this tokenization, all these tokenization spaces online? The reason that this jumps to me is because like you're talking about what are trade-offs that impact performance, and like ideally, presumably, you're picking the particular tokenization space that maximizes performance to cost. So like that does seem like an RL problem almost. So what do you have any thoughts on that? Like, could you do this online?
Yeah, so like,
is that too far off?
Like
is that
policy and the tokenizer?
Yeah.
That's a very good point. Yeah, I haven't given a thought on this, so I may not have a concrete answer. Yeah.
I mean, right, assuming infinite resources, right? Like you'd have 100,000 robots all performing different tasks, and presumably it would all wash out, and you could train them both together. Is that no?
I'm not very sure because I've never seen like people doing this. For example, like
no. I don't think anyone has. I'm just curious.
Yeah, so like in video and images, they also have this like first pre-train or VQVA or VQ GAN, things like that. Then you have like latent diffusion. Oh, by the way, speaking of this, like since the learned representation is continuous in latent space if you don't quantize them, so I'm also curious if you can just have a latent diffusion flow on this space. Yeah. I haven't given a try, but I would think this would be very interesting. But yeah,
very cool. Lots of things to think about. Very, very interesting. A lot of interesting ideas here.
I think there are a lot to think about.
Very fascinating.
So I think like whether you like action token. Yeah, so I think in general, like whether you like tokenization or you dislike tokenization, I think that's a must-have in the foundation model training pipeline, because that's how you can supervise your VOM backbone really well. But I'm not sure like if the future would be more like a fine-tune a video model inside of like a VOM model. But like if we were still stick with the VOM models, I guess tokenization is still necessary. It has to be there.
Well, yeah. Usually we end this episode by asking you what what papers you like, but it seems that you've already shown us a bunch.
Yeah.
Yeah. So yes. I
Yeah,
find
really
like
cool.
so I think like I hope I try to make like a comprehensive discussion on the history of action tokenization, say from just doing flatten the action chunk and pass the MLP to convolution to more recently have this register or learned embedding way to doing the representation learning, and to like other mechanisms, say improve the overlap rate to improve ordering by injection starting in our paper. So I try to make a comprehensive explanation or a brief intro on action tokenization, and also try to explain like how can we use action tokens in the future, or like training pipeline in general.
Yeah, and good. I mean, you wrote a very nice blog post on X as well about this paper.
Yeah,
I
thank
thought
you.
that was good, very, very good. Yeah, on top of the paper that you wrote, yeah, that was very neat. Yeah, I mean, it just strikes me that like, you know, if you, let's say if you're a VC looking at this space, you keep thinking, oh, you know, maybe scale data, scale hardware, or, you know, but oftentimes it's things like this kind of detail, like very, like how are you going to tokenize action that actually, you know, turns out actually drives reward performance. I mean, as we saw it from, I think behavior, right? Ilya, the team. So yeah, these things actually do matter. If you make the wrong design choice, it's like it's inherently quite limiting. Yeah,
Yeah.
very cool. Yeah. Okay. Cool. Any final things you want to add, Chaoqi?
Yeah, I don't have much more things to add, but yeah, I think I already discussed everything I want to share.
Okay. Cool.
Well,
Yeah. Well, thank you so much for coming on. This is really fascinating. I kind of feel that I need to go back and reread the paper one more time, just
Yeah,
to
please.
and then maybe listen to the
yeah, really
but
interesting
yeah,
stuff.
this is like I said, I mean, it's this kind of detail that actually oftentimes matters the most. You know, sometimes, especially when you don't have that much data anyway. Like this is actually quite significant, the improvement. So yeah. Okay. Thank you so much. Looking forward to your next one. Yeah, come back to the point again.
Thank you.
When you figure out the online stuff.
Yeah, certainly.
Okay.
Yeah, thank
Okay,
you.
thank you so much. All right. See you soon.
Yeah,
Bye.
bye.